Welcome to Part 8 in a series of videos on the drying of fruits and vegetables. In this presentation, we will examine mango drying. My name is Don Mercer, and I am with the Department of Food Science at the Ontario Agricultural College, University of Guelph. We will begin with several acknowledgements and a brief disclaimer. After an introduction, we will examine the drying mechanism and look at material preparation for the drying of mangoes. Then we'll move on to the effects of temperature and air velocity on the drying of mango slices. We'll look at conducting the actual drying runs and doing a test for doneness, and then we will finish up with some summary comments. I would like to thank Mr. Andrew Goodwin, Associate Industrial Development Expert with the Agribusiness Development Branch of the United Nations Industrial Development Organization, for his considerable efforts in coordinating this project. I would also like to thank those who are assisting in the presentation of this material to various local groups. Their contributions to our training activities are greatly appreciated. The author assumes no responsibility or liability for any problems of any nature encountered through the application of the principles discussed here. This material is intended for instructional purposes only. The purpose of this presentation is to outline procedures relating to the drying of mangoes. Although some of this information may appear in previous videos, it may be beneficial to have a centralized source of information that is focused on mango drying. As is the case in most drying activities, the key factors pertain to the temperature of the drying air, the velocity of the drying air, and the preparation of the material for drying. Additional influences include the design of the dryer, which may be a cabinet or tray dryer, and then we also need to consider air distribution and flow patterns within the dryer itself. We will assume that the design of the dryer is appropriate for the drying of mango slices, and that air distribution and flow patterns are uniform. Now we can move on and review the mechanism of drying for mango slices. We must keep in mind how drying of fruits and vegetables actually takes place. The most common errors in drying occur due to failures to recognize the fundamental principles. So you need to follow the rules, and of course, do not throw out the rule book. We must remember that moisture is lost from the surface of the material, and we can illustrate this with a simple diagram. Here we have a rectangle representing a slice of mango, and of course the moisture will be evaporated from the surface. In order to be removed from the material, moisture must travel from the interior to the surface by the process of diffusion. Diffusion is dependent upon the nature of the material itself. In porous materials such as apples, diffusion will be faster than it would be in a more dense structure. While mangoes are not as porous as apples, diffusion of moisture within the mango flesh is generally not a problem. In order to visualize the rate of moisture diffusion, you might want to think of it as the speed or velocity at which the water moves and compare it to that of a vehicle traveling down a road. So what we have here is the speed or the velocity dictating how fast this vehicle covers the distance that it needs to go. The faster the vehicle travels, the more distance it can cover in a certain period of time. So we can have the equation that the distance traveled is equal to the velocity times the time, and we'll let the time be 1 hour. So at 30 kilometers an hour, the car will travel 30 kilometers. And at 60 kilometers an hour, in 1 hour, the car will travel 60 kilometers. There's nothing really earth-shattering about this. Similarly, if a vehicle is traveling at a given speed, it will take less time to go a shorter distance than it will to go a longer distance, and this is quite obvious. So in our example, we'll let the speed be 50 kilometers an hour, and the time to travel 25 kilometers will be half an hour. The time to travel 50 kilometers will be 1 hour. So you need to relate this then to the diffusion of moisture in the slice of mango. There is really not much that can be done to alter the actual rate at which diffusion takes place. There may be some initial effects of temperature that can change the physical properties of the material, but this is rather limited. So we will not focus our efforts on this. We'll move on to other aspects. However, if we shorten the distance from the center of the material to the surface, this will decrease the time it takes for the moisture to travel from the interior to the surface. So here we have a thin slice of mango represented by this diagram and a thicker slice represented by this diagram. And in both cases, we've shown the center line as the dashed blue line. The distance from the center line to the surface naturally increases with thickness. So here in the diagram on the left, you can see that there is a rather short distance to travel compared to the distance from the center line to the surface in the diagram on the right for the thicker slice of mango. And the time for diffusion to the surface will increase as the thickness increases. The most convenient and logical way in which to prepare mangoes for drying is to cut them in slices. This is essentially dictated by the large flat seed. The mango should also be peeled prior to slicing, since the peel can reduce moisture removal and has a negative impact on the mouthfeel and chewing of the final dried mango slices. The question now is how thick the slices should be. No tests were done on mangoes themselves. However, experience gained with apples became the basis for preparing slices of other materials. And here we have a diagram that will illustrate the effect of thickness on the rate of drying, and these results are for apple rings dried in a forced air dryer at a temperature of approximately 55 degrees Celsius and an air velocity of 0.5 meters per second. In all of these trials, we began with an equal starting weight. The thickness of the slices were 0.4 centimeters, 0.6 centimeters, and 0.8 centimeters. Now we'll draw a horizontal line across the graph which indicates an equal weight of apple slices at some time during their drying process. From this, we can determine the time to reach the weight that is indicated by that horizontal line. So let's look at the 0.4 centimeter thick slices. We'll draw a horizontal line that follows the black dashed line across until it intersects the curve for the 0.4 centimeter thick apple slices. Then we'll drop a vertical line down until it hits the horizontal axis, which will give the time taken to reach that moisture content. Since we don't have any actual moistures on this graph, we will simply call this value T1. We can do a similar thing for the 0.6 centimeter thick slices and for the 0.8 centimeter thick slices. And as you can see, the thicker the slice, the longer it takes to reach this moisture content that we've indicated by that horizontal line. So now what we can say is, the thicker the slices of apples in this test, the slower they dried. The best thickness for drying, combined with ease of handling and preparation, was found to be 0.5 to 0.6 centimeters, or 5 to 6 millimeters. Here you can see the example of some mango slices in a dryer that are approximately 0.6 centimeters thick. And it should be noted that the peels were left on the mangoes here for testing purposes. Normally, they would be removed. Now let's take a look at the effects of temperature on drying. While the examples of using the speed of a vehicle may seem overly simple, they do have relevance in our consideration of diffusion. Let's consider what will happen to the speed of the car if the temperature around it changes. And the answer is very little, because the temperature really doesn't impact the speed of the car. The same is true with the rate of water movement through the material being dried. As stated previously, while there can be some changes in the physical structure of the material with an increase in temperature, the effects of temperature are limited beyond a certain temperature point. So what we're saying here is that there can be some influence, but it's really only up to a certain temperature. However, the temperature does have a key role in how fast the surface moisture evaporates. Once we reach this optimal temperature, there are very few positive effects of changing the air temperature beyond that. Excessive temperatures can promote case hardening, and excessive temperatures can also damage the nutritive value of the material. One of the most common mistakes in mango drying is thinking that increasing the temperature of the air in the dryer will increase the rate at which moisture is removed. Just because 55 degrees Celsius works well doesn't mean that 80 degrees Celsius will work better. Please do not fall into this trap. Here we have a graph of moisture ratio versus time. Please don't worry too much about the units on the vertical axis on the left. They are a way of comparing the moisture content of the mango slices so that we don't have to worry about the actual initial moisture content, and we can compare runs on a more consistent basis. What we have are mango slices that are half a centimeter thick and an air velocity of 0.5 meters per second. In the first case, the temperature of the air was 21 degrees. This was actually the temperature of the air in the room at the time the experimental runs were conducted. And you can see that the curve for 21 degrees Celsius moves rather slowly from the top left to the bottom right. Next, we have the drying curve using air at 44 degrees Celsius. And I chose this temperature because this is typically the temperature I would get in some of the solar drying experiments that I was doing. So there is a pronounced difference in the rate of drying in increasing the temperature from 21 degrees Celsius to 44 degrees Celsius. The red line is that for 50 degrees Celsius, and that's a temperature that we commonly use in many of the drying runs done in the lab, as well as going up to about 55 degrees Celsius. In the final run, we see the curve for 60 degrees Celsius, and it is the steepest one. But there are some cautionary notes. Do not be tempted to increase the air temperature beyond the range of 50 to 55 degrees Celsius, since this can create problems and reduce quality. And it should be noted that the drying rates at 60 degrees Celsius and above can vary from run to run due to case hardening. And this was actually one of the fastest runs at 60 degrees Celsius that I actually had. Most of them were a little bit slower and took upwards of about 8 hours to reach the final moisture content. You need to balance the rate of water removal by evaporation with the impacts of temperature on the quality and nutritional aspects of the final dried material. Now let's take a look at the effects of air velocity on the rate of drying. So in this case, we have mango slices that are 0.5 centimeters thick and an air temperature of 50 degrees Celsius. In the two drying trials that were conducted with different air velocities, we see what happens when we have a very slow air velocity of 0.2 meters per second compared with an air velocity of 0.5 meters per second, as shown by the curve in blue. The rate of drying is noticeably faster with the 0.5 meters per second airflow than it was with 0.2 meters per second air velocity. Tests were also conducted at 0.75 meters per second and 1.0 meters per second, but they gave only small drying rate increases beyond that of the 0.5 meter per second air velocity. Once the proper air temperature, air velocity, and sample thickness have been identified, conducting the actual drying run is really quite straightforward. Here we see some mango slices on drying trays going into a cabinet or tray dryer. The dryer should be started up in advance of placing the material in it. You need to be sure that the dryer is operating well. That means it's going at the desired temperature with adequate airflow and everything else is functioning as it should. It is easiest and fastest to load the drying racks when they are outside of the dryer. In this way, you can arrange the mango slices in an orderly fashion without having them overlapping each other. And in this case, we see an example of a run that is being done in a tray dryer. Since the mango slices will shrink during the drying process, it is okay to have them just touching each other at various points. You've seen this photograph before if you've looked at some of the previous videos, and here we have some fresh mango slices on a lab dryer rack, and in this case I have also not peeled the samples. After drying, you can see just how much the slices have shrunk in size. This will optimize the amount of material that you get into the dryer if you have them so that they just touch but do not overlap. Once the trays or racks are loaded and inserted into the dryer, you should begin timing your process. This will assist you in determining when you are nearing the end point. It will also give you a starting point for when to visually inspect the dryer contents during the run. If you detect an uneven pattern in the drying, it may be necessary to rotate the trays or move them from one level in the dryer to another. This type of inspection should be done at least every 2 hours. Some sources recommend using a higher temperature for the first 2 hours of the drying run, which corresponds to the constant rate drying period. This is not overly beneficial and actually can create problems if you forget to reduce the temperature, so my recommendation is to just stick with about 55 degrees Celsius for the entire run, and that way you don't have to worry about reducing the temperature after the first 2 hours. When you feel that the material is fully dry, and we'll discuss this in the section on testing for doneness, you can remove the trays from the dryer. You should allow the product to cool before packing it into containers, bags, or boxes, and this is because the warm material will often sweat and lose just a little bit of moisture that might be going into the bag, and that can promote microbial growth if it is trapped inside the container. You should cool the product in a room that is not humid in order to avoid the uptake of moisture during cooling. So here we have a warm, dry mango slice, and if there is a sufficient amount of moisture in the air, that moisture can actually be taken up by the dried mango slice as it cools. Sanitation is always an important consideration. The cooled product can then be packaged in airtight, moisture-proof containers with a good seal. This can include Ziploc plastic bags It can also include glass jars and any other packaging as long as it is airtight and moisture-proof. These containers can then be stored in a cool, dry area that is out of light, because sunlight can have a degradative effect on the product. So by all means, keep the product out of sunlight. Before we leave our discussion about mango drying, we should also consider how we determine the end point of the drying process. We have gone over this information in a previous presentation, but we should repeat it here for the sake of completeness. In a laboratory setting, we can monitor the process quite closely and predict when the material will reach the target moisture content, which is usually 10% on a weight basis. For small-scale operations which are not equipped with the same monitoring devices, this is a bit more difficult. Experience is really the major factor when it comes to determining the doneness or the final point in the drying process. If you dry the material at a moderate temperature of 50 to 55 degrees Celsius, you should be able to predict the end point based on the texture of the product. Here we have an example of some dried mango slices. Usually, the final product will feel dry to the touch and have a leathery texture. The dried mango slices will be pliable and they will bend easily without cracking. If the final material is too dry, it will become brittle and crack when bent. A visual inspection of the color can assist you once you know what a satisfactory end product looks like. So here we have examples of two dried mango products. The one on the left may be somewhat overly dried, as indicated by the dark brown color. Taste tests of the material will help as well, but you need to let the product cool down for a few minutes before checking it. This is because warm products tend to be softer than the cool products, and this can mislead you in your test for doneness. Once you have an idea of how long it takes to dry mango slices at the conditions being used in your process, you can monitor the mango slices closely as you near this final time. Once again, this is something that you will learn by experience. If you have suitable equipment for monitoring moisture levels, the situation does become easier. And here we have a laboratory moisture balance, which gives the moisture content to 2 decimal places, and that's a little bit more accurate than most people have for their endpoint determinations. So in summary, the following conditions are recommended for the drying of mangoes in a forced air dryer. You should have a slice thickness of approximately 0.5 to 0.6 centimeters. The temperature of the air should be approximately 55 degrees Celsius, and the air velocity should be about a half a meter per second. You may not be able to gauge the velocity of the air with any degree of accuracy, but you can do this by feeling the air with your hand. If you don't feel a sufficient amount of airflow, you will need to adjust the airflow to bring that level up. You should resist the temptation to use temperatures of 60 degrees Celsius or higher to avoid problems with case hardening and reduction of nutrition and quality attributes. You should also remember that drying involves many factors, including sanitation and product handling. Detailed records should be kept for all drying runs. And don't forget to learn from your mistakes as well as your successes. Thank you very much.